I'm back. All right, here we go. Now, from all this earthquake stuff, guys, one thing we're going to talk about is how we know the Earth's interior looks the way it does. This thing on page 10, Earth Science Reference Table. Major guess. We're not sure. We're not sure. The deepest hole we've ever dug. Wait, let me show you. Let me show you. On here. Oh, no. Let me get a tip of a pen. Here we go. Deepest hole we have ever dug. I'm about to dig inside the crust. Right here. There. See that dot I just made on that black line? Look at it. It's right there. No, you can't see it. You can't see it because it doesn't even show up. Knowing what's inside the Earth physically would be the equivalent of, let's say, that this floor is the top of the Earth and the ceiling of the school 3 floors down in the basement, okay, actually if we go down from here into the basement is the rest of the Earth. If I were to make like a little scratch of my fingernail, that's how much data we actually know in a physical way from observation as to what the inside of the Earth is like. We haven't scratched the surface. We have not scratched the surface. So how do we know there's an inner core, outer core, stiffer mantle, asthenosphere that was mentioned with all of its, look at, convection cells due to heat rising, due to heat falling, maybe 2,000 degrees there, maybe only 800 degrees there, still hot, but less hot than it is over here. And all that motion driving that white thing, which is the lithospheric plate, and the top of the lithospheric plate is called the crust, and the crust and the rigid mantle both make up what's called the lithosphere, the black line and the white line there. In fact, there's a slight boundary between the crust and the rigid mantle that's also been identified, this thing called the MOHO, named the Mohorchevich discontinuity. Why? Because of the way earthquake waves bend as they go through the Earth. I mentioned this before in one of the previous videos. We know what we guess as to what's here on page 10 from not direct data, but indirect data. We guess this from the way earthquakes bend, refract, that is, as they go throughout the Earth. And because of that, we think there is an inner core, we think there was a liquid outer core, going to show you that in a minute, and all the rest of these parts. You guys also have to know how to read this chart. I don't have time to bore you in this video with all that. Pretty easy though. Like if you go to a depth of 1,000 kilometers below the surface, and you go up right to 3,000, well, if you go right here, actually, let's not go right there. Let's pick on this one. Let's go to the beginning up there of the outer core stiffer mantle boundary. And you want to know what the temperature is right there. Well, what is it? The temperature is about 5,000 degrees. At what depth does it occur? About 2,900 kilometers. This is also atmospheres of pressure. What's the pressure like at the boundary between the outer core and the stiffer mantle? It's about 1.5 million times the pressure that we're on right now. Great scene in the movie The Core, where the pressure of the vessel that this guy's in loses its internal pressure, and all there is the external pressure as they're approaching the core. The thing that he's in just squeezes to nothing. Squeezes to the size of a pin. With him in it, very uncomfortable experience for him. Now, I want to show you how we think, why we think this is the way it is. So we're going to put on the lights, and we're going to go right here. In fact, we'll turn the overhead projector off. Follow me, guys, on this. We're going right over here to the whiteboard. So on the whiteboard, this is going to be the Earth, just like this. Okay, this is going to be the Earth. There's the Earth. Beautiful, round shape. Look at that. We're going to say that we have this outer core. And we're going to say that we have this inner core. And we're going to say that an earthquake has occurred someplace on the Earth. I'm specifically not going to make it at the top, because when I put it at the top, people think that earthquakes always occur at the top of the Earth right there. So I'm not going to make it at the top on purpose. This is going to be called the spot where the earthquake actually occurs, called the focus. This place is on the Earth called the epicenter. And this is why we think the inside of the Earth is the way it is. We're not going to deal with the Mohorchevich boundary. That's too small of a boundary, too insignificant compared to this outer core, inner core stuff in this big mantle. So what happens when there's an earthquake on Earth? Well, the P and S waves travel together. P plus S. P plus S. That stands for P and S waves. Now, if you're at City A over here, which wave will arrive you first? P wave, of course. They're always faster. S wave comes in second. And because we know the difference between the P and S wave, We can figure out on the chart on page 11 how far away the earthquake is. But we don't know where unless we have at least 3 of those. So, more P and S waves come out. P and S waves come out, traveling throughout the whole Earth. Whenever an earthquake goes off, these waves are going throughout the whole planet. So city B still getting its P and S waves. More P and S. More P and S. But here's the thing. This is unbelievable. The last time P and S waves show up together from any earthquake on the planet is 102 degrees on this side and 102 degrees on that side. What do we mean by that? You guys see how this is 90 degrees? Okay, 102 is bigger, right? So where that earthquake occurred, 102 degrees that way and 102 degrees that way is the last time P plus S waves are picked up by a city on the planet. This earthquake that went off over here. Now, what is about to happen, we're not exactly sure why it happens, but we can conjecture. P and S waves do enter this thing we now call the outer core. We think P waves S waves get completely absorbed. P waves have a heck of a time, but they do make their way through it. They're the stronger, they're the pulse waves. S waves are going side to side. They just get absorbed by whatever the outer core is. And then the refraction occurs every single time. I'm just going to keep talking, read through this
parents
person.
that are in the building picking up work. The building is about to close.
Every single time, 143 degrees later.
Have a good day.
It's okay, you just ignore that, and I'm just going to keep talking. 143 degrees later is the time that the P waves come out. Now, this is insane. P only. P only. No more S wave. Now, here's something we know for fact. We do know for fact that S waves can't go through liquid, because we can actually create artificial earthquakes, and we have seen underground tremors where P and S waves actually travel through oceanic waters and other underground subterranean waters, and S waves get absorbed and don't make it through liquid. Now, we do know that S waves can go through lava. So that means that lava has a consistency enough where it's not quite runny liquid, it's liquid-like, but it still has enough consistency that the S waves can actually travel through it. But S waves can't go through the outer core. Now, what are we saying here? S waves cannot go through liquid. S waves cannot go through the outer core. We put 2 and 2 together, that tells us that we think that the outer core is a liquid, and more liquid-like than magma, because S waves can go through magma. So it's a real liquid. P waves do make the journey. Now something else happens. Here's the P wave, here's the S wave. P waves enter, just P waves, because S are going to absorb through this inner part. They seem to really kick butt through that inner part. They seem to really move fast. And then they come out here, P only, of course, and P only, of course. But they show up at these locations faster than they should. Something made them go extra fast through the inner core. We do know that the closer atoms are in a substance, the faster that energy will vibrate by molecular collision through that substance. Conduction, that's called. P waves seem to pick up speed through the inner core. This leads us to believe that the inner core is solid iron and the outer core is liquid iron. And boy, you better know that. We believe that the outer core is liquid. And this also helps to explain the Earth's magnetic field, because now if we have a solid inner core being circulated around by a liquid outer core, that would be the rotational energy that's needed to generate ion differentiation, magnetic field. We think the Earth, the inside of the Earth looks the way it does because of all the refraction of this energy. Oh, by the way, the biggest earthquake ever in the world, 9-point-something, could have occurred at this city. If you live at those cities, or if you live at these cities between 102 and 143 degrees, you're the seismologist getting paid over $100,000 a year to figure this stuff out. your needle on your seismograph machine isn't even moving. It's not doing a thing. You're getting reports over your cell phone and over your computer that the world is going down. Crazy what that shadow zone makes happen, and the whole explanation of why we think the inside of the earth is the way it is. Thank you.